All right, this is AP Calculus AB Section B, Unit 2, Definite Integral, Lesson 6, Fundamental Theorem of Calculus 2. I must admit I was a little bit misled by the title. I was thinking this would be the Fundamental Theorem of Calculus in the second form, which is the integral of f of x from a to b is capital F of b minus capital F of a. But that was actually presented in a previous lesson. This is just some more expressions, more exploration into some of the implications of the fundamental theorem of calculus. Okay, so I've got two examples I want to give you here, and let's go ahead and do this here. So here's what I'm interested in. I'm interested in finding the area under the curve, or area between f of x, between f of x and the x-axis, or y equals 0. Okay, for f of x, and let's do f of x equals x minus, or x plus 1, x minus 1, x minus 4. Okay, from -1 to 4. Sounds like a fun problem here. So let's graph it, and I'm going to use a Desmos graph here. So I'll get rid of what was there before. Okay, so f of x equals x plus 1, x minus 1, minus 1, x minus 4. Okay, and we're going to limit ourselves to, be between, come on, won't let me get there, it's too close to the x, the closed window. All right, and so for x from -1 to 4. Okay, and let's have a look-see at that. Okay, back to if I zoom in standard, and then let's stretch it out horizontally from -2 to 5 here on the x-axis. -2 to 5. There we go. That's a good picture. Kind of helps to frame it, you know. All right, and now I'm going to just grab a screenshot, and we're going to work with the screenshot. Okay. So here's a screenshot of our graph. All right, here we go. Yeah. All right. And we're interested in the area between the curve and the x-axis. Now here's what's going to happen if I take the integral. If I just do the integral from -1 to 4, okay, of f of x dx, this is going to come out as a positive area, and this is going to come out as a negative area. And what I will get is the difference between the two, but the question is not asking that. What it's asking is, what is the total area between of the curve? And so it's important to recognize where it dips below the x-axis. And we're going to divide this into two regions. Now you can for this you could formalize it this way. You could take the integral, or actually let's do it this way here. You could take the integral, so the area is equal to the integral from -1 to 1 of f of x dx plus or minus plus the negative integral the negative integral from 1 to 4. And that's because the integral from 1 to 4 is going to be negative, and if we negate it, it'll be positive. The other option is we can simply add the absolute value of it, right? And that would take care of it as well. All right, let's go ahead and do this here. So the integral, let's figure out what this works out to. X plus 1, x minus 1 is x squared minus 1 times x minus 4. So x cubed minus x plus 4x squared plus 4 is x cubed plus 4x squared minus x plus 4. Okay, and the integral of that from -1 to 1 is x cubed, the integral x to the 4th over 3 over 4, x to the 4th over 4, I'm not going to have enough room, plus 4x cubed over 3 plus or minus x squared over 2 plus 4x. Okay, and that's from -1 to 1 plus or minus the same thing from 1 to 4. So x to the 4th over 4 plus 4x cubed over 3 minus x squared over 2 plus 4x from from 1 to 4. Okay. And I'm going to take it one more step, and then I think I'm going to go to the next example because I don't want to eat up too much time, and this really is something you can do. All right. So the next step would look like, and I'm just going to write it over here and write over the graph. It looks like A equals, okay, 1 to the 4th over 4 is 1/4, plus 4 times 1 to the 3rd over 3 is 4/3, minus 1 over 2, plus 4, minus, now I'm going to insert -1. So -1 to the 4th is 1/4. -1 to the 3rd is -1, so minus 4/3. -1 squared is 1, but it's minus anyway, so minus 1/2 minus 4. That's the first part. Minus. Okay, and insert 4. 4 to the 4th is 256 over 4. 256 over 4 is 64. Okay. And we got 4 to the 3rd is 64 times 4 is 256. So plus 256 over 3 minus 16 over 2 is 8 plus 4 times 4 is 16. That minus, okay, now insert 1. Okay, x or 1/4 and plus 4/3 minus 1/2 plus 4. Interesting, by the way, that these are the same because they are the same boundaries, and actually it should be this one. This one is the same as this one, and this one is positive, and this one's got a negative in front, and so they cancel out. So look for areas you can simplify like that. Actually, they don't cancel out. They don't cancel out because we get to distribute this negative in, and that changes to a positive, and then there's 2 of them. So no, it doesn't cancel out. And distribute this negative, this becomes negative, negative, positive, negative. And signs are probably the area where people make the most mistakes. All right, so I want to go into the second example here, and I'll leave this for you to finish if you like. But just the big idea that you need to, if you have an area under the curve, under the x-axis, you need to negate it or change the sign and add and find the area under the curve in parts. All right. Okay, so that said, let's repaste this function here, and let's place it over here. And I want to analyze. Let's say this is some function where defined by this f of x, or h of x. Let's do it h of x, because that's the way the lesson did. H of x equals the integral from a to x of f of t dt. Okay, and this is the graph. This is the graph of h of x. Or actually, this is the graph of h of x. And the question is, what does the graph of f of x look like? Right? Because if we differentiate h of x on x, if we differentiate, we're going to end up with the fundamental theorem of calculus being, actually, I'm thinking backwards. This is f of x. Right? Let me think about this for a second. Right. So we've got f of x, and we want to find h of x. Okay? So we've got some graph of f of x, and it starts from a, and let's let a be how about 2? Let's let a be 2, and let's talk about the graph of the integral. So we're going to start at 2. Okay, so here we go. We're going to start at 2, and the first point of interest for the graph of the integral is if I start at 2, what is the integral from 2 to 2? The integral from 2 to 2. We know the integral from a to a is 0. So the function value for h is, the integral is right here, right? Is at 0. Okay. Now as x proceeds to the right, the area of each slice, let's say x is right here. So let's say this is x. This total area is negative, right? So the graph is going down. It's going down. And as we move, x moves to the further to the left, it reaches this point where it reaches its lowest point, right? And it's accelerating. It's going down even steeper and steeper. And this corresponds to an inflection point in the antiderivative. Okay, an inflection point in the antiderivative. So we reach this point where the peak is, right? And there's an inflection point. So it's going down. Now what I don't have is the actual numbers. But it's going down here and reaches, it's going down steeper and steeper, but it reaches an inflection point. Here, let's sketch it better here. An inflection point right here. So where it's concave down in this region, afterwards it'll be concave up. Okay? And so there's an inflection point. Now it's still going down up here, right? And so when we reach here, the antiderivative, the derivative is 0. So that is a point that this is the derivative of f, right? Or the derivative of h. F of x is the derivative of h. Okay? Because remember, the derivative h prime of x equals f of x, right? So the derivative is 0. So that means the slope is 0 right here, right here. And so it's concave up and reaches a slope of 0. Okay. All right, let's take it the other way now. All right. So this has, let's say x is over here, and x now is to the left of A, right? To the left of A. And so this area is naturally negative. However, because the lower and upper bounds are switched, that negates it again. So it actually results in a positive value. So we now go above the x-axis. We go above the x-axis. And right here, the derivative f of x is 0. So that corresponds to a place where the slope is 0. Slope is 0, right? Okay, so we get something like this. Slope is 0. Okay, again, I don't know the specific values, but I'm just graphing a general idea of the shape. Okay, now here, the derivative, or the second derivative, is 0, right? The derivative of the derivative. And so that's an inflection point, right? And here the slope is positive, and actually the derivative is 0. Yeah. Got to think backwards, because we're moving to the left, everything is backwards. This is a positive area, right? But because the start point A is over here, the boundaries are switched, so the sign is switched. So it is going down from here on out, right? And where the derivative is 0 is right there. Okay? And now the derivative, the second derivative is 0. That's an inflection point. The first derivative is 0 here, and so it represents a place of horizontal slope. And there we go. So this is the derivative, or this is the graph of h of x, of h of x, or the antiderivative. So taking a derivative, we can find or sketch the graph of the antiderivative. Hopefully that helps. It's kind of fun to think of it.